Thank you, Alicia. So it's my pleasure to have the chance to talk to you today. I believe very strongly in the mission of the Autism Science Foundation. It's really an honor to have the chance to participate in the Day of Learning. So I am going to be talking to you today about, I'm going to be talking to you today about clinical biomarkers for autism. And I talk to you from two perspectives that Alicia mentioned. One of my roles, I'm a clinician. I run the Developmental Disabilities Clinic at the Child Study Center. And in my other role, I'm a scientist. I run a lab that does neuroscience research in autism. And wearing those two roles, I experience a problem. As a neuroscientist, I have many, many, many tools at my disposal. As a clinician, I have a tool. And it's the same tool that Leo Kanner had in 1943 when he first wrote about autism. We have our clinical eye. And the clinical eye can do many things, and we've come really far in terms of ways to refine clinical judgment, tools that can help clinicians be reliable at different places. But there are things that the clinical eye is probably never going to do, things that a clinical eye will never detect because they may not be evident yet. I can't see something as a clinician that hasn't emerged in a child's life yet. And there are some things that I might never see. There might be brain differences that are important, that have implications for treatment, but aren't evident in behavior. And I think that this is a limiting factor in our clinical progress. So I think what we need are biomarkers. Now, biomarkers can really mean many different things. A biomarker is anything that is an objective quantification of a biological process. So a biomarker could be gene-based, it could be a blood metabolite, it could be something in the brain. A biomarker could even be an aspect of behavior that's relevant to autism symptomatology, but it can't be evaluated through my clinical eye. It has to be evaluated in some kind of objective way. And why is this important? What will biomarkers help us do? So if we think of the group of people with autism as a really diverse group, right now we try to figure out how to help them based on our clinical judgment. We make decisions about treatment. We make decisions about prognosis based on our clinical eye. And I think the biomarkers might help us be more precise in determining which groups of children are more likely to benefit from a particular treatment, or which groups of children are going to succeed in response to particular treatments. So this is straightforward. I mean, we've got a room full of scientists and people interested in autism. This isn't news. So why don't we have biomarkers that we can use clinically for autism yet? I'm going to tell you 4 reasons that I think are important. 2 practical, 2 scientific. So the first practical is a universal problem, right? Any endeavor. If we are to find a biomarker that could be useful for clinical purposes, we need a biomarker that's really cost effective, right? If something is really expensive to measure, it's going to limit its public health impact. So that's one thing, economy. The second factor, which is kind of related, is accessibility. So for illustrative purposes, this is a map showing the currently funded autism centers of excellence in this country, and color represents distance to them. And so if I were to discover a biomarker that was really clinically important, but could only be deployed at places where there's a world-class autism center, you can see it would be limited in its impact, right? Not everybody could get to it. Now, for illustration again, this is a map that shows us every hospital in the country. And so if we were to have a biomarker that could be deployed at every hospital in the country, we could reach many more people and have a much greater public health impact. So those are 2 practical considerations, cost and accessibility. There are 2 scientific considerations that I think of as really central challenges in autism. One is heterogeneity. So autism isn't a thing. There is no brain profile for autism. There is no one genetic profile for autism, right? We're talking about many different kinds of things. So what does that mean for a search for biomarkers? How do you look for a biomarker for something that isn't a thing? You probably don't. right? What you probably should be thinking about is biomarkers in a different way. That we're not looking for biomarkers that are definitive of autism, but biomarkers are definitive of things relevant to autism. And what I mean by that is there are different domains of symptomatology involved in autism, and maybe there should be different biomarkers for those different domains. And I don't think it's a clinical problem to say that we're not going to look for a biomarker for autism, because that's not how we make clinical decisions. As a clinician, there is no treatment package that I prescribe for a person with autism. I need to know that person's strengths and vulnerabilities, and we make decisions that way. And the idea is that biomarkers could tell us the same thing about intact or impaired systems of function in the brain or in other aspects of biology of people with autism. So that's one scientific challenge. The second scientific challenge is development. So when we talk about autism, we're talking about something that isn't a 3-year-old, isn't a 30-year-old, isn't a 60-year-old. How do we look for a biomarker that's clinically useful across human development? How do we look for a biomarker that's clinically useful across the span of a treatment protocol? These are things that we don't even know in typical development. If I take an assay of brain function and I want to use it to measure someone's progress in treatment, we don't yet have an atlas for how that brain function should evolve over a 16-week course of treatment. So that's a real challenge. It's something that we need to think carefully about in autism. So I don't think that these challenges are insurmountable, and I want to tell you about the plan that I think could be useful to address them. So the first, to address the practical constraints, would be to use a technology that is cost-effective and that is realistically implementable. And one technology that I use in my lab is EEG. So the electroencephalogram is a recording of neural activity from the scalp. It's a great technology to use in autism because really you only have to tolerate wearing a damp hat. So it's very useful for people with high levels of comprehension, people with low levels of comprehension. It's a user-friendly way of measuring the brain. EEG is really cheap. So this is the EEG system that I use in my lab, and it's expensive to get that EEG system on site. But once you have that EEG system on site, it costs dollars to acquire data from a person. It costs salt water and latex gloves. So it's a cost-effective technology. And there are now, I would not feel comfortable using them in my research, but you can find commercially available EEG systems for under $100 now. So we're on the verge of having this be a really cost-neutral way of measuring brain activity in autism. EEG is also an accessible technology. There's an EEG system in every hospital in this country. We already use it at the population level for diagnosing seizures. We use it at the population level for screening in newborns for hearing their auditory brainstem response. So it's a viable, cheap, accessible technology. So I think we should be using these kinds of technologies to look for biomarkers. What about some of the scientific challenges? So this is 40 people. 40 people with autism would be a rock-solid neuroscience study in our field to date. Now, the problem here is that heterogeneity that I talked about, that is going to obscure my findings in a sample of this size. If some of the children have higher IQs, lower IQs, some of the children are older, younger, in 40 children, they will obscure my results. But what if instead of 40 children, I could look at 200 children, right? Then that noise can become useful information. I can take what would obscure my results and use it to refine my results. I can understand how the biomarkers differ in people as a function of IQ or as a function of age. So we can use that heterogeneity as informative variance. What about development? Well, we could study that too. So if we, instead of just seeing these children in a shot, what if we saw them multiple times? What if we saw them at a baseline, then we saw them 6 weeks later to see if these biomarkers are stable in the short term? And then what if we saw them 6 months later, so if we can see how these biomarkers change as a child becomes 6 months older, as 6 months pass and a child gets better in treatment? So these are things that we can study. So this is the plan. And I'm happy to report that this plan is not an abstraction. This plan is already in place. So I'm very excited to direct the Autism Biomarkers Consortium for Clinical Trials. This is a multi-site study. It's based at Yale.
and it involves Duke University, Children's Hospital of Boston, UCLA, and the University of Washington. And the idea of this study is to take the most promising biomarkers studied to date. So the biomarkers that have shown the most suggestive evidence of effectiveness in the smaller kind of studies that are prone to being vulnerable to heterogeneity. Then to do them in a big sample, in the longitudinal design, so that we can understand what works. How does development over the course of 6 months affect these biomarkers? How does it work for people as a function of individual differences? So that we come away with two things from this study. One, a set of biomarkers that have been vetted in a way that the field hasn't seen before. And two, a team. So part of the study is also really creating an incredible infrastructure, methodological rigor, where there's exact same technology, training by the exact same people across all these sites around the country. And so that's the idea. The idea is that we can take a big sample of kids, we can study them over time, we can use technologies, EEG, but also eye tracking, that are cost effective and implementable at scale, and make determinations about what works and what doesn't. We are about 6 months into data collection. Data collection will continue for a few more years, and we'll have some answers, I hope. So that's where I'll end. I'll end with a note of hope that I'll be invited back here in a few years, and that my first slide won't be the problem, it'll be the progress. So thank you.